Good evening, everybody. It's Mr. Copperhead here in ESUMS Engineering, and I want to go ahead and review with you the review sheet packet that we worked on in class. Just going to adjust my microphone a little bit. Hope that's a little better. Okay, so here's what we're going to do. We're just going to go through the items, and we're just going to work on the mathematics as needed. I've got my smart pen out, and I'm going to go ahead and show you some of those answers. So let's start with the easy questions here in the front. Which of the following is the correct term for a circuit that does not have a closed loop path for electron flow? So if that doesn't happen, where there's no loop, we call this an open circuit. All right. So an open circuit would basically be like if you had one with a switch in it and the switch was in the off position. That means that it's basically disconnecting the circuit. So therefore, it's an open circuit. Okay. A closed circuit is required so that it does allow electron flow. Question number 2. How much current would a toaster, 10.2 ohm toaster oven draw when connected to a 120 volt outlet? Okay, so this is an application of Ohm's law. So that's I equals V over R, right? And I'm drawing with my mouse here, right? Such talent, I know. So it's V over R, right? So if we're doing V over R, we're going to basically go 120 volts, okay? And then that's going to be over... There we go. And that's going to be over 10.2 ohms. All right. I'm just going to write out ohms there. You understand the symbol there is obviously something else. So we just have to do that math, right? Volts over ohms is going to become regular amperes. So we're going to go 120 divided by 10.2, and that's going to be 11.76. Did I type that right? Yeah, I did. 11.76, okay? And we'll go to the nearest tenth there. We'll go 11.8. So the actual current here is 11.8 amps, which actually is quite a bit of current, okay? That's a pretty catastrophic amount of current right there. So don't get shocked by that. Number 3, an ammeter. Remember, that's the device that registers or measures how much amperage is going through a circuit. It measures 2.5 amps of current in a wire that is connected to a 9-volt battery. What is the wire's resistance? So in this case, if I equals V over R, we would actually say that R equals V over I. So V and then over I, right? So we just have to take the current in this case and divide it into the voltage to get that particular value. So we're going to do this. We're going to say it's going to be 100, oops, in the wrong tool there, I went for that one. I want to do 9 volts, 9.0 volts, right, to indicate that we're going to use to the nearest tenth as far as significant figures is concerned. 9.0 amps, and technically over here, 11.8 maybe should be 12, but that's okay. And we're going to go 2.5 amps. So with volts over amps, our answer is going to be in regular ohms. So that's 9.0 divided by 2.5. That's just going to be 3.6 ohms. 3.6 ohms is not a whole lot of resistance. There are speakers that have more resistance than that. Most speakers are 8 ohm speakers. Some are 4 ohm speakers, so 3.6 ohms is still pretty low. Okay, so there's your first 3 questions, kind of concept related. Remember, we got that Ohm's law relationship that's used over and over here in all these problems. So here's number 4. Now, number 4 is a slightly different application called power, which we're going to focus a little bit more on after this quiz that we're going to take. Power equals current times voltage, okay? So power is rated in watts. We'll also learn a new expression for power next week as well. So a small electronic device is rated at 0.25 watts when it's connected to 120 volts. So what's the current of this device? Well, since we're looking for I here, we're going to solve this for I and say that it's P divided by V. So if it's P over V, that's going to equal our current. So power divided by voltage would equal current, okay? So in this case, it's going to be 0.25 watts, 0.25, and that's going to be divided by 120 volts. So our answer is going to be in amperes, but you'll notice that what's on top is smaller. So our answer is going to be divided, and we're going to get 20. This will be 0.00208, but again, since we want a number that's between 1 and 1,000, we're going to move this to the right and get 2.08. And since we moved it to the right, we would go down the ladder, so we would say 2.08 milliamps. Okay, not a whole lot of current, which makes sense because given the power rating is not that high either. So 2.08 milliamps is fine for that. We also could say 2.1 if we wanted to keep the significant figures accurate. We could say actually that it's 2.1 milliamps as well. Probably a little more accurate to say that. Okay, so what's the resistance of this device? Now, if the resistance is V over I, right? We know the current already, we know the voltage, and we know the current because we solved for it in the previous problem, right? So that means our resistance is going to be V over I, and our answer is going to be in ohms. So we're just going to take that, voltage from the previous problem and divide it by the current we got, which is 120 volts over 2.1 milliamps. Right, so we divide those two quantities. Our answer is going to be in kilo something, right? Because milli is on the bottom. So in this case, it's going to be in 50. So wow, look at that, 57.1 kilo ohms, or just 57 kilo ohms. Okay, so our answer here is pretty high, 57 kilo ohms, right? And again, this is, you know what? I'll draw the omega in this time here. Okay, so 50 kilo ohms. Let's go to a black marker here, and then we're going to draw my best sigma I can with a mouse. Not the best, but you get the idea, right? So 57 kilo ohms, very, very resistant to the flow of electricity here. Okay, now number 5, another kind of easy one here to work with here. Is it open, closed, parallel, or series? Right here, this is a closed circuit. Okay, so actually let's instead of doing that, we'll type it out. That's a closed circuit, right? And this is an open circuit because the switch is open, right? So we got a switch, we got a light bulb. Light bulb would not be on here. And here we have a parallel circuit. Okay, so parallel circuit there, close open there. The only one they don't show here is a series circuit, but wait, we turn the page and we see that we have a problem involving a series circuit. So we have four light bulbs that are on white bases, wired in series and connected to a power source. So we have a complete circuit here. These light bulbs would be on with this power source. And this is a 9-volt battery. It's connected to 4 light bulbs as shown on the right. So let's draw a schematic for this circuit. So obviously I'm going to use a combination of lines and on here, and I'll actually draw the schematic. I'm going to move this all down a little bit so I can draw the schematic above here, having a little more space here. So this is kind of what it looks like one bend here. We're going to have a power source here, which I will use a slightly thicker pen for. So here's our power source, right? And your schematic can vary, of course, that's fine. And then we're going to do this. We're going to go with a line here, okay? And I'm going to, if you'll allow me to, I'm going to use a, there is, of course, a symbol for a light bulb. I don't have one on my smart pen here, on my smart board. So I'm just going to kind of use a circle or circular type object to indicate a light bulb here, right? So with that, let's actually move that right over there as well, so we get that. And even these, I can move these as well. Let's see, there we go. That's good. And then again, I'm just gonna have 4 of these, right? 4 of these together. There's no resistors in between them, right? So, all right, you'll pardon the change in size here, right? That's not what this problem's about. As long as you just draw 4 light bulbs and make sure that there's no branches in the path, in the circuit path, then all is good, okay? You can even kind of draw it like this as well, right? It doesn't even have to be a straight path, right? And there's nothing wrong with that. So we put that circle there, and then we got just a couple more lines. So our schematic kind of look like this, right? And then let's draw one more line there. And then I'm gonna go ahead and connect a ground as well. So over here, and I'll connect my ground over here. So even though the ground's over here, it's there for stray electrons, but the electrons are going to want to go back to the power source. But understand the concept of ground there is so that there's no possible areas that the electrons could go, but that's besides the point. So there's a good schematic for that circuit. Again, these are representing light bulbs. What is the total equivalent resistance of this circuit? Well, the total equivalent resistance in a series circuit is just the sum of all the resistors, because the electrons all have to pass through it. So in this case, it's going to be 2.0 plus 4.0 plus 5.0 plus 7.0, which is going to be 18 ohms. So our total resistance is 18 ohms for this circuit. So with a total resistance of 18 ohms, I equals V over R. So for finding the current here, I equals V over R. So we're going to go I equals V, and then R on the bottom there. and then a nice little line right there. There's our formula. We'll use that a couple of times in this problem. Actually, we're moving it around for voltage, but I equals V over R. So in this case, the current is 9 divided by 18. So if it's 9 divided by 18, 9 divided by 18, what does that equal? Well, 9 divided by 18 is 0.5. So this is volts over ohms, so this is going to be regular amps. But we don't do that. We don't do 0.5. We would actually say 500 milliamps. But for the purposes of simplicity, when we do these calculations, I'm going to use the 0.5 amp, so that way our answer is in ohms. And you're allowed to do that. But just again, we would like to express these final current answers in regular engineering notation when possible. Okay, so find the voltage drop across each resistor. So we're going to just write a formula over here. We want voltage this time, so that's going to be I times R. So we're going to take the current and we're going to multiply by the resistor value at each point. So resistor 1, if we kind of go in this clockwise order, so this is going to be our 1 here, this will be 2, whoops, this will be 2 over here, this will be 3, and this will be 4. There we go. Okay, so 1, 2, 3, 4. So we're going to go in that order. So in this case, first problem, our current is 0.5 amps times 2 ohms. So if it's that, we're going to say it's 1 volt, right? We can do that. 1.0 volts, really, 1.0 volts. The next resistor is 4 ohms, so 0.5 times 4, that's going to be 2.0 volts. The next resistor is 5 volts, sorry, 5 ohms, excuse me. So 0.5 times 5, that's going to be 2.5 volts. And then the last resistor is 7 ohms, so 0.5 times 7, that's going to be 3.5 volts. So again, checking Kirchhoff's law, 3.5 times 2.5 is, sorry, plus is 6, then 2 plus 1, that's going to be 9 volts altogether. So all of our voltage is correctly distributed throughout this circuit. We got our higher voltage to get through the higher resistors, lower voltage to get through the lower resistors. So there we go. That's that next problem there. That's number 6. Now, this next problem is a parallel circuit. So understand that you have wires, and the way it's connected, the wires are basically connected in parallel so they can pass through the bulb or they can go through each other. So this particular parallel circuit is one also with 4 light bulbs. So if we draw a quick schematic to that, let's go ahead and do the same thing we did last time. Let's just move this down a little bit, give us some room, and let's go ahead and draw a quick schematic. So again, here's our power source, and I'm actually trying to draw the outline of this first right here. So there's, oops, there's that one, and then this is where the light bulb's going to go. We're going to put a light bulb there. We'll do the same thing here. That's 2. And then that's 3. Don't mind the non-straight lines. And that's 4. And then we're going to go all the way across here. We'll put a ground, we'll put a power source here to connect to here. And then we'll throw a ground down here. And let's get our pen out. And we'll go with power source right there. There's our power source. Down here is going to be our ground, right? Okay, and then over here is going to be our light bulbs, which we're going to go 1, 2, 3, 4. So there's our 4 light bulbs all connected in parallel. Okay, so because it's a parallel circuit, the resistance is going to be the reciprocal of the reciprocals. So we have to do the following. We have to go 1 over 7 plus 1 over 5 plus 1 over 4 plus 1 over 2. So see how it's the same light bulbs that we had in the previous one, just wired in parallel. So 1 over 7 plus 1/5 plus 1/4 plus 1/2, and then we're going to go ahead and make that the reciprocal, right? So let's do this. So we're going to our calculator. We're going to go 1 over 7 plus 1 over 5 plus 1 over 4 plus 1 over 2. And that's that, 1.09, okay? And if I do the reciprocal of that by hitting my reciprocal key, that's going to be 0.92. 0.92 ohms, okay? So R equals that. So again, what did I do there? Okay, so remember, with a parallel circuit, you have to do the reciprocal, sum of the reciprocals to get the total resistance for that circuit. So this circuit here, the components are all wired in parallel, so we could just use this calculation this one time right here. So 1/7 plus 1/5 plus 1/4 plus 1/2. Total resistance is always going to be less than any particular, even the lowest resistor in the circuit, as long as that's along a parallel path, which makes sense. Okay, so with R of 0.92, we're going to find the current in the circuit. That's I equals V over R again, right? I equals V divided by R. So what does that equal? That's going to be a, 9-volt battery divided by 0.92. So our answer is actually going to be greater, and this is going to be in regular amps. So this is going to be 9.78 or 9.8 amps. Okay, so current pretty high in this circuit with the way that it's wired. So now we're going to find the current through each resistor. So again, we're going to use the V over R equation, and we're going to get an amp reading, and hopefully those amp readings will add back to the total current that we just found. So the current through each resistor, let's do this. Voltage is 9, so the first resistor will go in order. So the 7.0 resistor is going to be first, excuse me. So 9 over 7, what does that equal? Whoops, what does that equal? Use our calculator here, 9 divided by 7. And we'll go with 1.3 amps for the first resistor. And the second resistor is going to be 9 over 5, and that equals 1.8 amps. And then we have 9 over 4, and that's going to equal 2.25 amps. Oops, let's move this into the box. And then this last one here is 9 over 2, which is 4.5 amps. All right, so with that, let's check our work here. 4.5 plus 2.25 plus 1.8 plus 1.3, we get 9.85. That's close enough. That's pretty good. Again, remember we did kind of round a little bit on both occasions, so it makes sense that our answer is not quite what we expected, but not quite what we got, but understandably very close right there. So good job. All right, so if you did all that, that's great. You got your parallel circuits, you got your series circuits. So let's see a couple of extra little tougher problems that we could also explore. So finding equivalent resistance, of combination circuits. A little bit tougher here, right? So finding equivalent resistance in the circuit shown in the figure below, all we're doing here is just finding that total resistance. Now understand, why is this a little tougher? Because this circuit is a parallel and series circuit simultaneously. We actually have a parallel circuit that's within here that if we calculate the individual resistance of this part here and treat it like it's a series circuit, we can add that to this and get a total resistance. Okay, so that's gonna be a little tougher. And maybe this might be, in some cases, depending on your class and teacher, this might be a bonus question. So that's gonna be pretty helpful to see. So here's what we do. We're gonna do the reciprocal sum and then get the reciprocal of these three resistors right here. So we're gonna go 1 over 18 plus 1 over 9 plus 1 over 6, right? And that reciprocal of that, and let's put parentheses on the front as well, okay? That right there is going to represent, if we think of this as one whole series circuit, this part here is going to have this total resistance right here. So let's find out what that is. 1 over 18 plus 1 over 9 plus 1 over 6. That's going to be that number, 0.33. So when I reciprocal that, I'm going to get 3. So that means that this particular resistance right here is only 3 ohms, okay? Now that's the parallel portion, right? The parallel portion, this 3 ohms right here, is basically this whole parallel block right here, which is just part of the circuit. So the electrons can either go through one of these 3 paths, but then once they do, they have to go through this path again, right? So this counts all, because all electrons must pass through this component. So the total resistance of this circuit is just 12 plus 3, or 15 ohms. Okay, so that's called a combination circuit. So when you have a combination circuit, you're going to want to find the parallel and series portions separately. Okay, now this next one over here is a little trickier. Why is it a little trickier? Because we have parallel circuit. Obviously, if you think of it this way, all the electrons must pass through this one, but then when they get here, they either can go down this path, which is just 7.0, or they can go all the way around and go through 2 resistors. So we have a little bit of a trouble with that as well. Okay, so let's go ahead and let's get this parallel part first. So what we'll do is we'll make this resistor, we'll think of this as having one resistor. So we're going to think of this as being 14 ohms here. So basically we're going to do the reciprocal of a 14 ohm resistor and a 7 ohm resistor, because it can either go down this way or it can go down all the way for both of these. So we're going to do 1 over 14. We're going to go text tool here. First thing we're going to do is we're going to go 1 over 14 plus 1 over 7, and we're going to do the reciprocal of those, and we're going to do the -1 there. Okay, so we'll do that. Calculator, 1 divided by 14 plus 1 divided by 7, and then we're going to do the reciprocal of that, and that's going to be 4.7. Yeah, 4.7. We'll do that. Okay, so equals 4.7 ohms. All right. So that means, now again, that means that this particular circuit, this whole parallel part right here, okay, from here and here and here, right, that's all 4.7 ohms. So we can treat it as if it's just one resistor that's 4.7 ohms. So the rest of this is in series. All the electrons have to go through here. They can pick a path and then come back and they have to go through this one again. So that's going to be 7.0 plus 1.5 plus 4.7 for a total resistance of 8.5 plus 4.7 is 13.2 ohms. Okay, so that is the total resistance in B. But for number 9, same kind of deal, except again we have two parallel paths, each with their own series circuits. 90 and 10, 90 and 10. So what do you think is going to happen here? With the total resistance of 60 ohms, what does the total resistance end up being? Well, again, we're going to treat each of these as having 100 ohms of resistance. So it's going to be 1 over 100 plus 1 over 100, right? Which is just going to be 1 over 50, right? And we're going to do the reciprocal of that. But we're going to keep it written like that just for that. So that's going to be 0.02, and we do the reciprocal of that. That's going to be 50 ohms, which makes sense. All right. Now, if the total resistance of the circuit is 60 ohms, this resistor must be what gets us to 60. So if it's 50 already from this path, this one here must be 10 ohms. So 10 ohms for that resistor. And that's that, okay? So I hope that this was helpful. I hope you enjoyed this video, and I hope you do well on your electronics quiz. Have a great day.